A very good morning to you, student. Today I'm going to discuss some more basic definitions related to this linear concurrence. Okay, all these are from Unit 1. I just want to discuss this thing with you before I start with this linear concurrence explanation on linear concurrence. So here this division algorithm theorem is said. It is an important theorem. What does it say? It states like this: let A and M belong to the set of integers with M greater than 0. Remember, M greater than 0. Then there exists a unique integers Q and R such that A is equal to MQ plus R, where R here is greater than equal to 0 but less than M. What does it mean? Here it means that when you divide A by M, then there always exists a unique integers Q and R. M here is a positive integer, Q and R such that A is equal to MQ plus R, where R here is greater than equal to 0. Remember, this R must be greater than equal to 0. It is not negative integer because M here is a positive integer. So it should be strictly less than M. So this A here is called the dividend, M is called the divisor, Q is called the quotient, and R is called the remainder. So for example, if you take A here is equal to 7 and M is equal to 3, divide A, this 7 by 3, what we have to find according to this theorem, you have to find unique integers Q and R such that 7 can be expressed as 3Q plus R. So for that, when you divide 3 by 7, what you have here is 7, you divide it by 3, 3 2s are 6, the remainder. So there exists a unique integer Q is equal to 2 and remainder R is equal to 1 such that 7 can be expressed as 3 into 2, that is A is equal to MQ plus R, where R here is remainder is equal to 1. Now in case A here is equal to 6 and M is equal to 3, then there exists a unique integer Q, means only one integer of that, only one quotient for this which satisfy this relation, that is Q is equal to 2 and R is equal to 0 such that 6 can be expressed as MQ plus R, where M here is equal to 3, Q is equal to 2 and R is equal to 0. So which is same as 3 into 6. So in this case, since the remainder is equal to 0, what does it mean? It means that 3 divide 6. Okay. So in general, if A is any integer belong to set and you divide it by an integer M equal to 2, then that A can always be expressed in the form A is equal to 2k or A is equal to 2k plus 1, because in 2k here means A here is equal, when you divide an integer A by 2, so there exists a unique integer Q is equal Q and remainder R such that A is equal to 2q plus R, but R here the divisor is 2, so the remainder must be greater than equal to 0 but strictly less than the divisor M. So the possible values of R must be either 0 or 1. So when R is equal to 0, you have A is of the form 2k. When R is equal to 1, A will be of the form 2k plus 1. So therefore, when A here, then if every integer is, if M is equal to 2, then every integer A equal to 2 is exactly of the form, okay, this is the next one, when A is equal to 3. So this shows that when A is equal, A for any integer A, you divide it by 2, then that integer A will be of the form 2k or 2k plus 1. It depends on this, using this division algorithm theorem. And now if M is equal to 3, then every integer A belong to set. When you divide it by M equal to 3, then that A will be exactly of the form 3k plus 1 or 3k plus 2. Why? Because by division algorithm, there exists an integer Q and remainder R such that A can be expressed as 3Q plus R, where the remainder R takes the values either 0, 1 or 2. It cannot be negative value. Remember, this remainder R is always a positive integer. So it takes the values 0, 1 or 2 because it is strictly less than 3. So therefore, if R is equal to 0, then it is of the form 3k. If R is equal to 1, this A will be of the form 3k plus 1. If R is equal to 2, then it is of the form 3k plus 2. So in general also, if you divide it by any integer, so it will the form, suppose M is equal to 4, it will be of the form 4k plus 1, 4k plus 2, 4k plus 3 and so on. So let me recall again this definition of concurrent, like in the second video that I have discussed with you is that what is the concurrent is you take m greater than 0 be fixed positive integer, a, b belong to set, then we say that a is concurrent to b modulo m if m divides the difference of these two, that is a minus b, and we write a is concurrent to b mod m. We also said this b here is also called the residue of a modulo m. So, or in other words, if a and b, if a and b are two integers such that when you divide it by m, it leaves the same remainder, means you divide a by m, it gives you say remainder r1, and when you divide b by m also it gives you remainder r1, then we say that a and b, they are concurrent modulo m, that is a is concurrent to b modulo m. So here next there comes the greatest common divisor, because all these things are needed in linear concurrence. So before I start, before I explain to you the linear concurrence, I want to discuss with you some of those basic definition like the divisibility definition, concurrent definition, and the greatest common divisor, that is g.c.d. So in the greatest common divisor, first let us see this note, the number of divisor. When you divide any integer a belong to set, then the number of divisor of this a is always finite for a different from 0. Why? Because if a is greater than 0 and d divides a, then this divisor must be less than or equal to a. It cannot be greater than a. So the number of positive divisors of a is always finite. If d divides a and d is less than 0, then in that case also that minus d is a positive divisor of a, hence the number of positive divisor of a is always finite. Similarly for the case when a is less than 0. Next, if a and b belong to set not both 0, one of them only can be 0 but not both of them equal to 0, then the number of common divisors of a and b will always be finite. Common divisors of a and b, for example, if you take a is equal to 6 and b is equal to 3, what are the common divisors of a and b? So a here can be expressed as 3 into 2. And b here is equal to 3 into 1. So from among this a and b, what are the common divisors of a and b? Common multiples of a and b, they are 3 and 3. So therefore this is called 3 is called the common divisors of a and b. And then the other one is 1. So the greatest of all these divisors of a and b is called the g.c.d of a and b, or the HCF. In schools you have, instead of greatest common divisor, we call it as highest common factor. So here let us see the definition. Let a, b belong to set not both 0. The largest of the common divisors of a and b is the greatest common divisor of a and b, and we write g is equal to ab, where g stands for the g.c.d of a and b. For example, if you take a here is equal to 12. A is equal to 12. What are the common divisors of 12? 2 into 3 into 4. Sorry, 2 into 3. 6 into, sorry, let me write. A is equal to 2 into 2 into 3. That is 2 into 2 into 3 is 12. And if you take b here is equal to 6. So 2 into 3. So from among this, what are the common divisors? 2 and 2, they are common divisor. 3 and 3 also that are common divisors. So 2 into 3 is 6. 2 into 3 is 6. So the greatest common divisor of a and b is 6. Okay. That is the multiple of this. 2 into 3, that is 6, is the greatest common divisor of 12 and 6. And some of here, there are some of the basic properties of g.c.d. If a and b belong to set not both 0, and let g stands for the g.c.d of a and b, then for this g, the g.c.d of a and b can always be expressed as ax naught as a linear combination of a and b, that is g is equal to ax naught plus b y naught for some x naught y naught belong to set. And g here, this greatest common divisor, will be the smallest positive integer of the form ax plus b. All the proof of this are in unit 1. I'm just giving you the statement only. The proof it will be discussed by the other teacher who is supposed to take unit 1. Now, third property is that if you have any order divisors, d divides a and d divides b, then and g is the greatest common divisor of this, then d must divide g. For example, in this case, if you have A here is equal to 12 and B is equal to 6, what are the greatest common divisor of this? The GCD of A and B, that is equal to 6 here. And you know that 2 is also a divisor. 2 also divides 12. 2 divides 6. 2 is another divisor of A and B. So it implies that 2 must divide the greatest common divisor of this A and B, that is 6. So so this statement means that if there exists another common divisor of A and B, and G is the greatest of all this common divisor of A and B, that common divisor must divide the greatest common divisor, or the GCD. And if you have M is greater than 0, then the GCD of MA and MB is same as M times the GCD of A and B. Remember this notation, round bracket, A comma B denote for the greatest common divisor of A and B. In schools, we call it as HCF, or the highest common factor. Next is, if GCD of A by G and B by G is equal to 1, then the GCD of A by G and B by G is always equal to 1. Why we can talk about A by G? Because G always divide A, since it is the greatest common divisor of A and B. So therefore A by G will be an integer, say L, and B by G is also something, say K. So that's why we can talk about the GCD of A by G and B by G. Now, if the GCD of A and B is same as the GCD of B and A, is same as the GCD of A and A minus AB, is same as the GCD of A and B plus AX for some. All this will be discussed in Unit 1. And if GCD of A and M is equal to GCD of B and M equal to 1, then the GCD of A, B with M will also equal to 1. Next, the last property is that if A divides BC and GCD of A and B is equal to 1, it means that A must divide C, because GCD of A and B is equal to 1 means that the only common divisor of A and B here is equal to 1, which shows that A cannot divide B. So this implies that the only possibility is that A must divide C. That's all.